Hello gems, welcome back to another video. This is the question bank series. With this series we are getting 10 questions stronger in every BITSAT chapter. Okay, so today we are discussing the chapter of EMI, not the one that you pay to your coaching institute. Uh, we have electromagnetic induction. Okay, so here firstly we discuss the previous year trends and then we move to the questions, right? So you know the drill. If you have missed out on the previous lectures, we have done quite a bunch of these chapters. Okay, so check out the playlist in the description box of this video. So let us see the previous year trends. So from this chapter we'll see Faraday's law, Lenz's law. On their basic concepts questions are framed. So 6 questions from there, mostly questions from induced EMF are asked. Also on motional EMF we have 4 questions, inductance 5 questions, so you have mutual and self inductance, right? We'll come to the questions, and finally LR circuits 2 questions. Okay, so that is the previous year trend. So let's hop into the questions now. We have question 1 and 2 over here. In question 1 we are given flux as a function of time. They are in standard units, phi is in Webers, T is in times. We are supposed to tell what is the time when the current will become 0. So flux is given as, so the EMF, induced EMF will be d phi by dt, right? And this EMF in turns gives current, right? IR, if the loop is closed, if you have a closed circuit, this EMF will tend to give a current. Okay, so when this EMF becomes 0, basically the current will become 0, right? And when will EMF become 0? When d phi by dt becomes 0. So that is what Faraday law is, right? There is induced EMF if there is a change in flux, right? Change in flux with respect to time. So if there is no change in flux with respect to time, there will be no induced EMF, there will be no current. So first find d phi by dt, and the negative sign is just telling the polarity. So just equate the magnitude to 0. Okay, so d phi by dt. So anyways, even if you have the negative sign, you can take it to the other side. So equal to 0, right? So let's take the derivative. So 4t, 2t square. So t square derivative is 2t, right? So that 2t and this 2, 4t. Then 6t derivative is 6 and phi is a constant. So we'll equate this to 0. 4t is equal to 6, t is equal to 6 by 4, or cancel it, 3 by 2, which is 1.5 seconds, which is option B. Let's come to question 2. Here we have a magnet which is being released along a vertical axis. This is passing through a coil. Okay, the coil is conducting. Okay, of course, so it will lead to a current. So because the flux is changing, right? You are dropping the magnet. So when it is far, flux is less. Far here, when it's close, flux is more. So flux is changing. There will be induced EMF, and you can see it via Lenz's law. Okay, so you are supposed to comment on the acceleration. What will happen to the acceleration of this magnet? You might have seen certain experiments on YouTube wherein they drop certain ball from a rod. Okay, and it takes a while to drop, right? Because this is in fact the concept that will be used here. Okay, so if you know those type of video, it's surely less than the g. Then let's find out the reason for it. Okay, so as this magnet, for initially if you see, when the magnet is you can say approaching the coil, okay, it will increase the flux, right? North side, it will increase the flux. Okay, so on the top side of the magnet, it will according to Lenz's law, it will oppose its cause, right? The induced EMF will oppose the cause. So since the flux is increasing through the coil will induce that EMF in a way that will oppose this change. Okay, so the coil will induce a current in this direction, right? In the anti-clockwise direction as seen from top. So the field lines will come out. Okay, so north pole is making the field lines go inside. More and more field lines are going inside. So the opposite effect is current in this direction, magnetic fields outside, right? So the coil will try to decrease the flux, opposite. Okay, so what will happen? This will put right. This will have a north pole on this side. So north and north will kind of repel. So the magnet will slow down. Okay, and what happens when the magnet is going away? Same thing you can see. Okay, so now the magnet is going away. So less and less lines are going inside. So now south pole is going away, right? Here north was approaching, so the magnet, so the coil created a north of itself, don't come, don't come. So opposite effect, that way you can think. And here the south pole is going away, now coil will be like don't go, don't go. Okay, so it will oppose the effect. So now since south is leaving, it will create north. Okay, so in both cases it is creating north, just in the opposite directions. Okay, when you see, okay, so it will create north and will again try to pull it, right, attract the south pole. So yeah, that's the logic behind slowing it down. Okay, so the acceleration, the effective acceleration, if you see, will be less than g, right? It will slow down as it is falling through the coil. Okay, you can see certain experiments on YouTube too regarding this. So that's about these two questions. Over to the next. 3 and 4 over here. In question 3, we are asked for the dimensional formula for magnetic flux. Okay, so you can try this as an exercise. Okay, I'll write the formula BA. Okay, you can try, you can pause the video here and try it as an exercise, see how much time it takes you. It's a question from simple dimensional analysis. It will tell you your hold on dimensional analysis. Okay, so you might think it's easy, right? So phi is equal to BA, so A has meter square. Oh, what is magnetic field? How do you get that? Okay, you might go in the direction of Biot-Savart's and this and that and mess it all up. Okay, you can try it. Okay, I'll reveal it. The way to find the dimensions of magnetic field in 1, 2, 3. B is, or you can write in terms of force. Force is L cross B, right? So you can find the dimensions of B from here. It's quite simple now. B will be force by IL. Okay, and I is standard, right? So force is mass into acceleration, ml2 t raised to minus 2, and this length, and what is I? I is ampere. Okay, so this length and length gets cancelled, mlt raised to minus 2, a raised to minus 1. So those are the dimensions of magnetic field. Now phi will be mlt raised to minus 2, a raised to minus 1, and area is L square, right? Something going wrong, oh, sorry, these are the dimensions of energy, right? Force is mass into acceleration, acceleration meter per second square, right? Yes. So here we won't have a L, and here it will be magnetic field into area, right? Area is L square, so now we'll get L square. So this matches with option A, right? ml2 t raised to minus 2 into current. Okay, so basically if you see energy into current, is there some formula like that? You think about it. Let's come to this one. Here we have a coil which has a area A naught is placed in a magnetic field which changes from B naught to 4 B naught. So either the area can change or the magnetic field can change in order to change the flux, right, or to induce EMF. So here also the average induced EMF, average, right? So you could need not worry about the small integral and all. You just take delta phi by delta t. Okay, so what is delta phi? First of all, you can see that these two options, even dimensions are not matching, right? B into A, that should be the dimension. So B into A by T, right? So delta phi by delta T, induced EMF. So what is the change in the flux? Okay, flux is given as BA. So that is write it. Phi 1 will be, in first case, it is B naught, B naught, A naught. So area is not changing. And a second case, the magnetic field is becoming 4 times B naught, A naught. Okay, so what will be this? Phi 2 minus phi 1, right? Changes phi 2 minus phi 1. So 4 B naught, A naught minus B naught, A naught by the time taken, which is T naught, right? This happens in a time interval T naught. Okay, so average you are supposed to do. So 3 B naught, A naught by T naught is your answer, which is option A, right? So that's about these questions. Over to the next one. Question 5 over here. Here we have a loop, metallic loop, square of side this has a resistance of 1 ohm, okay, and it is moved with constant velocity v, and we have a magnetic field inward, okay, and field and the square plane is moved like this, okay, so it's a square frame, okay, and you are supposed to tell a magnetic field value is given if the current flowing through this assembly is 1 milliamps, okay, what should be the velocity, okay, what should be this V, so that the current that we get, whatever way it is flowing, should be 1 milliamps, okay. Now the magnetic field is uniform over here, it is not changing. So you might ask how it is giving rise to an EMF, because we have BVL, right, the motional EMF, right, B, and it is V cross L. So if you see V and L, all of them are perpendicular to each other, only then it will have the motional EMF. So B, so what is the EMF? IR, right? R effective we'll have to write, and this is BVL. So we are supposed to find this velocity, right? So what is the magnetic field? It is 2, and velocity we are supposed to find, length is 0.1. The current is said to be 1 milliamps, and what about the effective resistance? Okay, R effective. So if you see, this is a Wheatstone network. I hope you know to find the resistance of this. It will be simply 3, right? All of them are equivalent, and this one is pretty much useless. Okay, so 3 plus 3, 6, 3 plus 3, 6, 6 and 6 in parallel, 3. Okay, so in a Wheatstone bridge, if you have all equal resistances, basically the answer will be 3. The answer will be whatever the value of the one resistance is. Okay, provided all are equal. Okay, and now we'll have, so this is 3, and mind you, it is not 3 actually, 3 plus 1, right? So there is also resistance in this assembly, the square, right? So 3 plus 1, okay, it is 4. So you might tend to make a mistake over here. So this is 4, okay, and this is 2 into V into 0.1. Okay, we are supposed to find V, so we'll have 2 milliamps, or 2 to the power 10 to the power minus 3, and V into, this is like 10 to the power minus 1, right? So 2 into 10 to the power minus 2, right? And this is in meters, right? Because we had substituted, this is in meters and this is also in meters. Okay, so this answer is in meters. Let's convert it to centimeters. So 10 to the power minus 2 is centimeters, right? And this is meters per second, so this will be centimeters per second. So basically 1 by 100, right? 1/100th of a meter is a centimeter, right? Or 1 meter is 100 centimeters. Okay, so yeah, that's your answer. Don't forget about this resistance as well. That might lead you to a wrong answer. If you had plugged in 3, it would have given you 1.5, right, which is not there. Good, okay, but it might lead to an error if they purposely give an option with that choice. Okay, so be careful when you do such questions. Okay, so certain data might be provided in the question and certain over here in the figure. Okay, so you have to keep in mind both these things. Okay, so that's about this question. Over to the next one. So question 6 and 7 over here. In question 6 we have been asked when will electric potential be induced between the ends of this rod PQ, okay, when it moves in a certain direction. Okay, so magnetic field is shown, it's from L to Q. Okay, so along what direction should this rod move so that an EMF will be induced across this ends, right? So if you see, if EMF is induced across this length, here magnetic field is like this, EMF will be like this. Okay, if we have the velocity in m direction, right, we should have everything perpendicular, right, B, V and L. So the length is along this direction, suppose, plus minus we can have, so the length is along the direction P. Okay, then the magnetic field is L to Q, so that is also taken. Okay, L to Q, all the usernames are taken. Only one that is remaining over here is the M one, right? So, or the concept is all this should be perpendicular, VVL. Only then we have the EMF, right? The motional EMF. Okay, so it can't move along the length. So along length and this, if it moves like this along P, length vector and this this motion will be in the same direction, no EMF. If it moves along the magnetic field again, how will it produce the potential difference, right? When it moves like this, all three are perpendicular, and we have the EMF set up. Okay, so option D should be correct. Okay, all the other indices are for the other vectors. Okay, V should be along M. Let's come to this one. Here we have a current that falls from 5 to 1. If the average induced EMF is this, what is the self-inductance? Okay, simple formula based question, L di by dt, right? Because EMF in a coil is given by, so single coil we have, so self-inductance, right? And of course there is a minus sign, but we are only concerned about the magnitude. Okay, okay. So L is what we are supposed to find. So average, so you can write actually delta I by delta t, right? So delta I is 5 minus 0, 5 time, okay, is 20, falls in a circuit. Let me check the time. The time should be given in 0.1 seconds. Okay, this happens in 0.1 seconds, so divide by 0.1. So let's take it to the other side. So 20 by 5 into 0.1, this 0.1 and this can get cancelled, or you can cancel this by 4 and 0.4, right? Or anyways 2 by 5 is 0.4. Okay, are we doing some mistake? Is this the correct units? Okay, this is 200. My bad. So let us do this calculation. So 10 times, right? So 4 Henry. Okay, but let's do the calculation. So 200 like this, right? 200 into 0.1 by 5. So 5 fours are and 0. This 0 and the decimal will shift. So 4 Henry is your answer, which is option E. Okay, so that's about these two questions. Over to the next one. Discuss question 8 and 9 over here. In question 8 we are given the current, which is current in the inductance coil according to the graph. I versus T graph is shown. You are supposed to tell what will be the variation of voltage. Okay, now you know current, you know the relation minus L di by dt, right? So change in current is, if you see di by dt is constant over here, right? Slope, because I versus t, right? So the slope is nothing but the derivative, right? So in the first half, suppose this is the first half, we consider the slope is positive, slope is negative. So first half, what will we have? EMF will be, now slope is constant, right? So it will give some constant value. L is a constant, and di by dt in the first half in this region will be some positive constant. So this is positive, this has a negative sign, this is also positive. Okay, these two are positive constant and we have a negative sign. So in the first half it should be negative. Where is that? Only in this graph. Okay, and you'll see that it should be constant, right? Because the slope is remaining constant, is not changing with time. Okay, at least in the first half. In the next half it is becoming negative, similar in magnitude but opposite. Okay, right? So this will become negative, di by dt is negative now, and this negative will make it positive, and so it will gain a positive value at this point. So there is a discontinuity, or you can explicitly integrate this, but yeah, that will be slightly tough. But yes, you can see, right, slope is positive, and this is so this is positive, this is positive. The formula itself has a negative sign, so negative EMF, and then the slope is negative, positive, and that is the constants are positive. So this is the graph that is correctly represented. Okay, no one else has a negative region in the first half, right? You could directly do this question by only analyzing half the part. Okay, let's come to this one. Here the options were given, but it might make it too too messy over here, so I have made it Ronaldo. No, so I've made it, we'll write down the answer finally. Okay, so three circuits are given. There is L element and also a C element. Okay, the coil and resistance. Okay, so we are supposed to tell the current order, or the current order in this case and this case. Okay, respectively. So just after closing the switch. Okay, so just after closing the switch, the current will try to grow. right? There is no current in the circuit when the switch is open. Once you close the switch, the current will start to flow, right? You can see. So once you close the switch, current will start to grow, okay? And uh, the coil does not like a direct change, right? It will slow it down. So the coil works on the principle of Lenz's law, right? So whatever change is happening, it will oppose it. If the current is trying to grow, it will say don't grow, okay? So here when we just close the switch, the current is trying to grow, right? It wants to shoot to that value of I by R, okay, or I by 2R in this case, okay? So the coil will slow down this process, okay? Of course, over time it will attain that value, but for initially, just when the switch is closed, the coil will oppose that. So what will happen, this coil basically at the initial time, just when the switch is closed, you can treat it as an open circuit, okay? So you can just open it because it won't allow initially, it won't allow the current to grow, okay? So thereby completely stopping it, okay? So just open the circuit. So if you see at if you open the circuit, there is no path for current to flow, okay? So I1 should become 0, okay? Let's see for this one you'll have to open this branch, right? Current can still flow in this branch. This branch it can't flow because the coil will oppose the change and it will open up, okay? So here this is what is happening, okay? So it will open the branch, okay? So just like there is open branch over here, okay? So this will open the branch. Current cannot flow from the outer branch, but it can flow over here. So the current in the second case is E by R, right? E by this resistance R, okay? I'm using V is equal to IR. So I3, let's find that out now. So again, we'll have to open this branch in the first case, okay? So if you open the branch, you'll see the current will be E by 2R, okay? These two are in series, so same current is flowing, right? So they are in series, so E by 2R. So you can find the relation, right? So which one is the I3 is in between. If you see I1 is 0, so it is the least one. 231 will be the relation, okay? I think it will be same for the other case. Let's check, but so I2 will be E by R, I3 will be E by 2R. Both are finite values. I3 is less than I2, right? Half, and I1 is 0. So that is almost, that is lesser than both of them. Okay, these two are positive constants, right? So now let's come to this one. When the after a long time, the current will make its way out. Okay, so initially, of course, the opposition on the coil is great, but as time passes, it adapts to the change, right? There is a steady state. If I'm going into the technicalities, so it will attain a steady state after a certain time. So a steady current will flow, which that will also depend on the resistance of the impedance of the coil, okay, or what is it called, reactance, actually, reactance of the coil, but we will treat it as ideal and will consider the impedance or the reactance of the coil to be 0. We will only consider the resistance in this case. So I1, if you see, so basically we will remove the coil. Okay, we are treating it as ideal, or otherwise after a long time we will replace it by whatever resistance it has. In the question it's not mentioned, so it is a ideal coil, okay? So just now, so initially we had open up the circuit, now you short circuit, okay? So you just close it, okay? You just remove the coil. Initially you remove the coil and keep the circuit open, now remove the coil and join it, okay? So that is the logic for these two cases. You can keep that in mind, okay? So now when we join the coil just by a wire, okay, so if you have a simple wire in this place, so you'll see that the current will be I1 will be E by 2R, right? Now I2 will be, just replace this coil by a wire, so these two will become in parallel, right? This and this will be two separate branches, okay? So these two are in parallel, so I will be E by R, and R in parallel is R by 2, right? R by 2, or this 2 you can take on top. It will be the current in the third case, okay? So again short circuit this. So once you short circuit this R and 0 are in parallel, okay? So if you see the current over here. The current has a choice of going from the zero resistance path and the path where there is some resistance, right? If there are two resistance, the current will split among them, okay, in certain ratio, so that um, the potential difference is kept constant, right? In parallel, potential difference remains same, right? So, but here there is zero resistance over here, coil is removed after a long time, and here there is some finite resistance. So the current will entirely pass through this. So it's as if like this resistance is not there. Or you can use the R effective formula. R effective, okay? What is R effective in parallel? R1 R2 upon R1 plus R2. Okay, what is R2? R1 is R, R2 is 0. So this is 0. So the effective over here is 0. So basically this is a line when this coil is removed, okay, after a long time. So only resistance we have is this one. So this will be E by R. So now you can arrange them in the ratio. So you'll see that 2, 3, 1 again, right? So 2 is the highest, right? 2 in the numerator. Then we have 3. So in between these two, and this is the half. Half of 3 is 1. So again 2, 3, 1. And here sign is this way. And here I1 is not 0. Okay. So this was also there in the question. Okay. There were other options as well wherein the same order was maintained and this was non-zero, okay, and this was 0. So it had to look for that also. Okay, so quite a good concept testing question. So I hope you understood it. If not, rewind and watch it back. Okay, so you get the grasp of this concept. Okay, and that's about these two questions. Over to the final question for the week. Question 10 over here. In this question we have a rod of length L. This is that rod. It is moving. So we have motional EMF. It has resistance R. So the length has resistance R, speed V. Okay, so it is moving like this. Magnetic field is inward. So as I said, we have motional EMF. What will be the current through this assembly? Okay, or through the coil. So you can actually construct a circuit out of it. So of course there were options, but they are a mouthful. So let's directly find the answer. So R and we'll have like, so instead of this rod we can imagine this resistance R naught. These are R1 and R2. So and we have some induced EMF, right? So we are making a circuit out of this basically, because anyways the role that it is playing, the concept of EMI is used over here is just the induced EMF, right? The motional EMF. So this is that motional EMF, and we have R1 and R2. Okay. Now the motional EMF is given by BVL, right? We are supposed to find current. Current will be we can find the current, right? So R by E by R effective. Okay. Now this might seem complicated circuit. You might go for Kirchhoff law and blah blah. Okay, but you trust me, you don't need to do that. Okay, it can be solved quite simply. Okay, we are supposed to find current, right, from here. So if you see these two are actually in parallel, right, R1 and R2, because the potential across them is same. Okay, Kirchhoff's law would have been useful if there was a resistance here, somewhere. Okay, there is no resistance here to make a drop. So here we have the same potential here and here, here and here, here and here. So these two have the same potential. Okay, are connected across the same potential. So they are in parallel, right? So R1 and R2 are in parallel. So their equivalent will be R1 R2 upon R1 plus R2, right? Product upon sum. And now the circuit becomes, now it's very simple. So here we'll have epsilon or E. So this is R naught and this is that. This I'll call R dash. Okay. So this is that R dash. Okay, so these two in parallel we have solved. So this is R dash. Now R dash and R naught, we have come across this type of circuits. They are kind of an illusion. You might think they are in parallel, but they are in series, right? Because the same current is flowing through them. So whenever you are deciding series or parallel, please check if the potential is same or the current is same. So that is the separating criteria, right? That is how you derive the formulae, this and the series one, sum. Okay, so yeah, that is what you are supposed to look for. So this R naught now, so R effective basically will be this R prime plus R naught, right? They are in series, same current, right? And the current is what we are supposed to find. So let's find R effective first, because that is how the questions proceed, right? Whenever you have a circuit, you first find the R effective, and E by R effective will give you the current, right? So that is the idea in every current electricity question. So this is our R effective. So EMF is BVL, and this here will have R1 R2 upon R1 plus R2 plus R0. Okay, so let me check, is it in the same way? Yes, it is in the same way. Okay, no modifications done to the options. Okay, this is the very option that you will arrive at. Okay, by the way, the questions are from Photo Club book. Okay, all the questions for the question bank series came from that book. Okay, it's quite a relevant source for BITSAT, and we've been using that and will continue to use it for the rest of the series. Do join me, and that's about today. Okay, I hope you really enjoyed today's session. I'll see you soon in the next video. Till then, keep enjoying physics.